Weak acids, unlike strong ones, do not go to completion. So, for example, if we have a weak acid like HA and we put it in water, we're going to get some ionization. The hydrogen is going to go with water to form hydronium plus the anion. This is going to be way less than 100% ionization. So equilibrium is entered. The reaction continues to go back and forth. So if we have an acid like formic acid with this formula right here, if you've ever been stung by an ant, it burns, and that is formic acid that the ant injects into its victim. Formic acid when it reacts with water, a little bit will form hydronium plus the anion formate. This is very much unlike hydrochloric acid, which goes to completion. This is 100%. Formic acid ionizes a very small percentage. So we can set up an equilibrium constant. We're going to take the products over the reactants. Water will not be in the equilibrium expression. Okay, let's clarify a few things that chemists talk. This is called an equation, like a balanced equation. Even though this has an equal sign, chemists don't call that an equation. We need to distinguish. So we call that an expression. Just so you know, that's how we distinguish things. Well, when we measured the pH of a 0.10 molar formic acid solution, the pH measured with our pH pen was 2.68. Once again, that is 2 sig figs. So 10 to the minus 2.68 is 0.0021 molar. That's the concentration of our hydronium. So now we want to figure out what are the concentrations at equilibrium. So when we talk about an equilibrium expression, all of these concentrations of hydronium, of an anion, of an acid, those are all at equilibrium. Again, when we say acid, we're referring to the original acid, not necessarily the hydronium. So let's write our equation over our icebox. So our original concentration of our acid is 0.10 molar. Water is not going to factor into the equilibrium expression or calculation. For the sake of the calculations, we say that the acid and the anion are 0 to start. So we're going to use this value that we calculated. That's how much the hydronium concentration goes up once it reaches equilibrium. Because there's a 1-to-1 ratio, the anion is going to go up the same amount, and the acid, again, 1-to-1 ratio, is going to go down that same value. So at equilibrium, we can write out our concentrations at equilibrium. And then calculate Ka. using the equilibrium expression. Since I've already written it once, I don't need to write it again. So we would take the hydronium times the anion, formate. Since they're the same, we'll just square it. Over and we get a Ka value of 4.5 times 10 to the minus fifth. Now, if we look at the above equation and we were to add water, we added more water, would the pH go up or down? I'll let you think about that. What about the Ka? Will it go up or down? Well, think about what Ka stands for. It's a constant, right? So it shouldn't change. Any changes are due to experimental variations. Well, let's say we were to add some water. Let's say we were to add 3 milliliters of water to 3 milliliters of our acid. Let's figure out what the concentration is of the acid after mixing in the water. We'll use M1V1 equals M2V2. M1 is going to be our original concentration, 0.10 molar. That's our acid. V1, we used 3.0 milliliters. M2 is what we're solving for, and V2 is the 3 plus 3, which is 6 milliliters. Now you could probably do this in your head, and you know it's going to be half, but you'll be doing some calculations similar to this in the lab, and they're not as easy to do in your head, so I'm going to go ahead and work this one out. So that's going to be 1.0 times 3.0 divided by 6.0, and we get 0.050 molar for our acid. When the pH was measured, it was 2.82. So 10 to the minus 2.82 is 0.0015 molar. That's the hydronium concentration. So now let's do the ice table. So once again, we added water. So what's that going to do to the hydronium? So let's take a look. We started off at 0, and that's again for calculation purposes. Our acid concentration, that is the concentration after mixing. Okay, so whenever you're asked for the initial concentration, it's after the dilution or after the mixing. All right, so we went down by the hydronium concentration, and these went up. Again, everything is in a 1:1 ratio. Okay, so now let's go ahead and write the equilibrium expression. We've done this before, it hasn't changed. but it's always good to practice. And generally on quizzes and exams, we always want to show the equilibrium expression. So now we'll plug in the numbers. These are the same again. And the Ka that we calculate comes out to 4.6 times 10 to the minus fifth. Looking at the previous calculation, we had 4.5 times 10 to the minus fifth. So it's not a drastic difference. That's fairly close considering the tools that we're using